What do quantum mechanics and a 10 million year transition have in common? The answer lies in the heart of hydrogen's 21 centimeter line. So in this problem, 1133 out of the extras for chapter 11, we're tasked with the spontaneous emission rate for the 21 centimeter hyperfine line in hydrogen out of section 7.5 can be obtained from equation 11.63 back in perturbation theory, except that this is a magnetic dipole transition, not an electric one, which was covered back in chapter 7. So what we want to do is the electric dipole needs to be shifted based on this magnetic moment here over C due to the the dimensional analysis of it. A lot of yin yang in the E and M field stuff, as we saw back in the electrodynamics book. But now we see that we have this as a state composite of spin up, or the triplet state and the singlet state, with the magnetic moments for the electron and proton added together vectorially. And here you see that the electric and magnetic moments, or the magnetic moments of electron and proton, are given as such. Here we have the G factor up top. And this is, of course, the moments we just talked about. 0 and 1 are the singlet and triplet configurations given back in chapter 4. And then because m sub p is much greater than the mass of the electron, the proton contribution is negligible. So, since we're looking here, we can get rid of that term altogether. And so the spontaneous emission rate here is given as such, where this is the matrix element that we need to find. And so the task is to work this out, use whichever triplet state you'd like, and put in actual numbers to determine the transition rate and the lifetime of the triplet state. And the answer is given here. Okay, so a little bit cut out for us, and we see here that we care because we saw how critical this hyperfine structure was back in chapter 7. Now we get to see the magnetic moment that was such a breaking discovery back in, I want to say, the 70s, the 60s, something like that, come into fruition here. Now, of course, it's been a while since we've seen chapter 7, so what about the electric dipole transition that was talked about back in chapter 7 and 7.5? That being said, pretty short question actually after we get through the initial setup. So if you want the PDF, that also will be posted to the Patreon page, or I can send you the link to it. Whatever works best for you, you can definitely acquire it, no big deal. Just let me know. And then before we jump into today's topic, you should know that my goal is to break down complex physics concepts using exercises from top books. If this sounds like something you'd enjoy, hit subscribe and join us in exploring the universe. Now on to the 21 centimeter line. So let's talk a little bit about the setup here and why this happens in the first place. So, as you saw, this problem refers to the 21 centimeter hyperfine transition in a neutral hydrogen. Okay, and this transition occurs between two hyperfine levels of the ground state. So we're already looking at something really, really small, all things considered in the energy gaps. And so this was in the ground state of hydrogen. And the energy difference between the two levels corresponds to a photon, which is what we see here, being emitted with a wavelength of 21 centimeters at the frequency of 1.42 gigahertz or 1,420 megahertz. Just multiply by 1,000. And so what we're looking for actually is the transition with the magnetic dipole transition, not the electric. And the rate of spontaneous emission for this transition is given by Fermi's golden rule. So we need the probability density and things like that that we saw briefly. And the expression for the spontaneous emission A was given to us, so we're cool there. So as you see, what we have to realize here is that the states of both the proton and the electron play a role. In particular, the triplet states for the hyperfine splitting correspond to the electron and proton spins aligned. So you see we have up arrow, up arrow. And then you see that the singlet state corresponds to when they are not aligned. So up arrow, down arrow, and hence the spin flip. So now that we have the kind of the idea of what's going on here, where you see that the triplet state denoted 1, singlet state denoted 0, we can go ahead and use this setup and then evaluate the numbers directly. And the numbers are definitely weird. Okay, so Now, when we go to choose our triplet configuration, we're told we could choose any of them. So let's take a flashback to chapter 4. So here we see that all this says is that the triplet states need to have the spins aligned. So I could be up, up, and then the other natural answer would be down, down. That's pretty easy. But because we know we're quantum mechanics, we could also be the superposition of up, down, down, up. Okay? The weird stuff in our heads that makes this go round, we just have to have faith in it. But this is a plausible answer by all the probability metrics, so we're good. So we choose the up, up, which again, that came from 4.175, and then the singlet state is given as a single entity, so that is a 4.76. So we know we're up, down, down, up. Okay, and so now that we have our configuration figured out, what triplet state we wanted, now we can go ahead and try to evaluate the matrix element. So we see that the one state we're up, up, easiest that we could be, although you'd get the same result for the down, down, and the same result for the mixture, and we'll see why in a second. And then here we have SE, which again, the bold tells you you're a vector operator. So flashback to chapter 7 or chapter 6, and the selection rules there too. Moving forward, we see that this is nothing more than the inner product of the vector operator with the combination of states. So factor this out. Now you see that and apply the factors to both sides and distribute accordingly. The constants come outside. We have up, 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 down, and then the SE in the middle. Good to go. Minus sign, of course. Now, what we have to realize here is that since the electric dipole doesn't affect the spin of the proton, the first term evaluates to 0. Okay, so that goes away, and we don't have to worry about it since we have something acting on the electron, which is changing its spin state. You can't raise an up arrow. Okay, so this goes away, and that leaves us with 0, and now we're broken down into only this part here. So let's go ahead and break this down a little bit more, and then get to solving. Okay, so now that we have that and we know what we need to do, again, realizing that the electric dipole doesn't affect anything on the protons, we can just collapse them and not worry about it. And now we're left with the electron and spin up and the electron and spin down for the transition to occur, which makes sense. As we saw in the diagram, it was spin up, then it went to spin down. This is what we're looking for, the transition of this via the magnetic dipole. So this all makes sense. So while the setup took a little while to get to, what do you think about this? Drop a comment below with your thoughts because this is a lot to deal with and not exactly self-evident. So moving forward, upon this simplification, we can now address the vector nature of this operator. So the dipole here is broken down component-wise. So you have the electric dipole in the x, y, and z directions. Put that in the angle bracket notation, not to be confused with the inner product. And then recall that we have the raising lowering operators that can combine to make us into Sx and Isy components. We saw that with angular momentum as well. So, and just, I believe linear momentum as well, yeah. So definitely angular momentum. So we've seen this schematic before. And so by adding together the up and downs, we see that we can get a plausible vector operator for the SE in the x direction, and then simplify that down, easy enough. And then you have the same thing for y, just take the difference here, more tools, divide over the 2i, and you're good. So once we have that, then we can go ahead and plug in the fact that the magnetic dipole for the electron is a vector operator into the inner product, and then we could take them part by part. Okay, so since we know we're a vector, we can put them, instead of in the ijk notation, we could put them as a column vector for x, y, z here. Go ahead, plug in their raising lowering operator definitions, knowing here that z is not going to do much to us, so we're fine. That's a separate eigenvalue question. And now what we can do is use the process of linearity to clean up these brackets here and then evaluate part by part. So get the constants out front, what we do here, no problem. Go ahead and use the linearity to split these up, plus in the middle, minus in the middle, z stays put. And now we could start to see what's going to cancel out. Let's take a note of a couple things here. Go to blue. This is plus on a down, good. This is down on a down, bad. Plus, down, good. Down, down, bad. Remember, we can't lower a down arrow and we can't raise an up arrow, but we can raise an up arrow, or we can raise a down arrow or lower an up arrow. So that's why we saw that we could pick any of these states and these operators would cancel them out due to what is allowable. Okay, so as promised, since we had down, down, or up, up, one of those combinations, we get zeros there for those arrows. And now we saw that the effect of that is by changing the down arrow to an up arrow, we got a factor of h bar. Changing down arrow to up arrow, we get a factor of h bar. And now both of these have a factor of h bar, which we can factor out, noting that here the z direction is already in alignment, so we don't have anything to project on. So that goes away. Now moving forward, we can clean this up, get rid of everything. We see that the inner product of two similar states gives you 1, so we're good. Now we see that we're just tidying up with algebra. Both terms or all terms have an h bar over 2. Factor that out, 0 stays put. We love that. We don't like i's in the denominator, so rationalize that. That's where you get the negative I from. Multiply by I over I. Then from there, we see that the magnitude of this matrix element squared is equal to the conjugate or dagger conjugate, which is conjugate transpose. So that'll affect this column vector. The constants all real, these all real, so this will be flipped and turned to a positive. This then will be multiplied into it, and we will get our scalar answer. All right, so square the constants, good. Take the transpose, take the conjugate, perfect. Now we see that we have a row vector and a column vector, so this looks like our dot product, row to column multiplication, 1 to 1, positive I to negative I, 0 to 0, good to go. Negative goes away, h bar gets squared, 2 gets squared, that square root and square cancel, so we get a 2 here, no big deal. Simplify down, this goes to 1 minus I, 0 still there. That negative I, or that I squared goes to negative 1, so the negative negative cancel, perfect. Positive 1, so now you add them together, you get 2, 2 and 2 cancel. So you get a familiar answer of h bar squared over 4. We saw that back in chapter 4 plenty. Okay, and that came from the square operators. Very, very nice. Nice to see how things come together. All right, so we found our matrix element for this in the magnetic sense, so P sub m, and we're good to go. This leads us straight to step 2, where we can kind of fast forward and get through everything else pretty quickly. Now with the matrix element complete, we can find the spontaneous emission rate, which was given, plug it in there, cancel away where you see fit, and now you see that you just join everything together. That is your spontaneous emission rate, and we're done. Okay, thankfully that was given to us, but you could have used Fermi's golden rule to find it. The next big step here is to identify the omega, because that's where the energy is going to be given. Remember in the beginning of the chapter it was EB minus EA, right? So we're going to have that all over h bar. And from that, we can go ahead and simplify this and find a lifetime. So although this is nice, we still need the frequency from the energy exchange from the 21 centimeter transition line. So given that we have EB minus EA over h bar from omega, that's delta E, put it there. Now you see that the omega, which is the frequency that we have access to, and the energy level, we were able to solve for the energy level, and it was given to us in the question. So now that we have this and it's cubed, plug it into the transition rate, cancel everything down, simplify it. We want to simplify it as much as possible here because then the lifetime, tau, is just 1 over the transmission rate. Dividing by a fraction, multiply by the reciprocal. So now you see you have everything here. Now, if you want to plug these in by numerical values, I would suggest using a quick Python script. Just plug them in, let it execute it. Or Mathematica, because the standard calculator will get overflow with all the scientific notation and the weird powers. Use something to your advantage. The c to the 5th, me squared, h bar squared, e to the 3rd. and all that. That's a lot for the computer to handle or the calculator to handle. So use a computer, and then sure enough, you get with some rounding errors. I just rounded it for what the book gave us, and you get 1.1 roughly 10 to the 7 years, so about 10 million years. That's quite a bit. So clearly, this thing is not going to happen like we think it is. But nonetheless, we found the transition time and lifetime, so we're good. And that was a very curious problem. I like to break down the mechanics of it all because just saying triplet state, singlet state, and not showing where we came up with them or why things went away, I think those are important details that we need more of. So, that being said, that was a fun problem, and I will see you on the next one. All right, that was fun. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also want to take a moment just to thank my incredible Patreon supporters. Your support truly is the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions makes a real difference in helping me bring these concepts to life, and I'm grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.